It can be fun to power your electronics project using a solar panel like this, but how do you know if you're extracting and utilizing all of the power that a panel is providing? My name is Zach and I'm the Byte Sized Engineer. In this video, I'm building a maximum power point tracking solar charge controller. The best place to start when trying to understand maximum power point tracking are the specs printed on the back of your solar panel. In this case, I'm going to be using this 100-watt solar panel, and the specs that I list here are going to be different than the panel that you might be using. The first piece of information I want to know about this solar panel is its open circuit voltage. This is the voltage that is measured across the terminals when no load is applied to the solar panel. In my case, that's 24.3 volts. The second piece of information I want to know about my panel is the short circuit current. If I take the positive and negative terminal of the solar panel and I connect them together, the current that I measure running through the wire is the short circuit current. In my case, that short circuit current is 5.2 amps. Now obviously these numbers aren't true if I have the solar panel indoors like this. These values are what the panel would produce under standard test conditions. But in the real world, these numbers will be different depending on the amount of sunlight, how many clouds there are in the sky, the temperature, and a whole bunch of other factors. Solar panels operate on a power curve. That is to say, the amount of power that they can produce is dependent on the amount of load attached to them. And if you remember, power is equal to voltage times current. So when there's no load attached to it, the voltage is at 24.3 volts and the current is at 0, therefore the power it's producing is 0. Similarly, if I attach these two connectors together and put an infinite load on the panel, the current goes up, but the voltage drops to 0, and therefore the power it's producing is also 0. To get power from a solar panel, we want to be operating somewhere in the middle of that curve. I threw up some temporary mounts for the solar panel, and as much as I'd like to film out here in the sun, I actually attached a long enough cable and I'm going to feed it through my window so that I can work and film inside. The first thing I want to do is measure the open circuit voltage, or VOC, with no load attached to the solar panel. And to do that, I've got a multimeter here and I'm just going to measure across the positive and negative terminal. Okay, so in current conditions, my VOC, my open circuit voltage, is 21.8 volts. This is the open circuit voltage right now in time. This is constantly changing and it will change depending on the conditions outside. To measure current, I need to switch over to current mode. And I'm going to short out the circuit using the multimeter and measure the current. My short circuit current right now is 3.7 amps. So far, we haven't pulled any power out of the solar panel. So to do that, we need to hook up a load. And to make things a whole lot easier, I've installed a little electric energy meter in series with the panel. This is going to tell me the voltage and the current at any given point. Once I connect up this load, I want to sweep it across its whole range and collect all of the data points so that I can put them into a spreadsheet. My goal is to be able to plot the points so that we can see the power curve. To start, I'm going to attach a small load of 40 ohms. And you can see that the voltage dropped a little bit, but I am pulling about 11 watts out of the solar panel. So if I increase the load, you'll see that the voltage will continue to drop and I get 15 watts out of the solar panel. Okay, so let's keep increasing the load. Now I'm getting 22 watts out of the panel. Let's keep increasing the load. Okay, I'm at about 40 watts out of the panel. If I keep increasing the load, the voltage continues to drop, but the power increases. I'm at 45 watts, 50 watts, 53 watts. And then if I keep increasing this load, the voltage continues to drop, but now the power is also dropping instead of increasing like it was before. So that tells me that we have reached that maximum power point. So what we want to do with our charge controller is to be able to find that maximum power point where we're pulling out as much power as we can out of the panel and always track that power point because it's constantly changing. It's never going to be the same from minute to minute. Let's see what that looks like on a graph. I watched back the video and I plotted some of those points that I saw, and here's what that power output looks like as we adjusted the load. On our horizontal axis, we have voltage measured in volts, and our vertical axis is power measured in watts. When there wasn't any load attached, our open circuit voltage was 21.8 volts. As I started to increase that load, the voltage started to drop slightly, but we started to produce power. And as we continued to do that, our voltage continued to drop slightly, but our power continued to increase until we got to 17.6 volts. Our power output at that point was 53 watts. As we continued to increase the load, our power started to come back down. So our maximum power point for that particular situation was 53 watts, and it happened to be at 17.6 volts. If I were to do this even now, 10 minutes later, I would get a slightly different curve. This is sort of a sweet spot for this particular panel under these conditions. So the goal of a maximum power point tracking solar charge controller is to make sure that that load always stays at that sweet spot. Let's say that we connected a buck converter to the solar panel and dropped the voltage down to 12 volts to charge a battery. That buck converter will just be operating at some fixed voltage, which is not necessarily the maximum power point. And so you're not necessarily getting the maximum power out of that solar panel under those conditions. Previously, I made a video where I went into great detail about how buck converters work. So if you're not familiar with their operation, I recommend watching through that video as a refresher. A buck converter would work to do this as long as you could control the duty cycle and thus control the output voltage. And that's what I initially tried to do. I built this buck converter switch mode power supply. I used an Arduino to control the duty cycle of a MOSFET, but I couldn't get this to work very reliably. So what I did was I went onto the DigiKey website and I searched for maximum power point tracking integrated circuits. And of course I found one. The chip that I'm going to use to design my own maximum power point tracking charge controller, that's too much of a mouthful. From now on I'm just gonna say MPPT, maximum power point tracking. The chip that I'm going to use for my MPPT controller is the BQ24650. I opened up the data sheet and I found the typical application circuit, and at its heart it looks very much like a buck converter with a few extra parts. From there I can just use the typical application and design my own custom PCB. For the schematic layout, I just put down the BQ24650 and I follow the typical application circuit and I place all of these components. The benefit to using this chip is that I can program the maximum power point by providing a voltage on the MPP set pin. The voltage is controlled by this voltage divider, and all I have to do to change the voltage is to use a digital potentiometer and a microcontroller. The microcontroller that I chose to use for this project is the Adafruit ESP32 Reverse TFT. It's got a TFT display as well as 3 buttons, so I can write a nice little UI for it. I want to be able to measure and monitor the voltage as well as the current, so I'm going to use the ADC pins on the microcontroller to measure voltages, and then I'm going to throw on some current sensors on there that the microcontroller will use to read the current. The board layout took a little bit of extra care because there are some high-speed signals here, and when there are high-speed signals, you need to make sure that you're following good PCB layout practices. There's a lot of good notes in the datasheet for this, and I just followed those carefully as I laid out the components. I ordered these boards and I also ordered a solder stencil along with it, and now it's time to apply the solder paste to the boards. And to do that, I'm going to use the stencil that I ordered, and normally what I would do is I'd get some old PCBs and I would line them up and give myself sort of a frame or a little jig to put my PCB in, and then I would have to manually align the solder stencil with the pads on the PCB. But this time I decided to try something new. I designed and 3D printed a little jig that I can stick the PCB in, and then it automatically aligns the stencil right where it needs to go. I'm not sure if this is going to work. This is the first time I've done it, and of course if it doesn't work I can just go back to my old method, but I figured it was worth a shot. I think the proper technique is to get all of the solder paste in one squeegee wipe, but I'm not that good at this, so I'm having to kind of go over it multiple times and kind of cleaning up and filling in spots. Before lifting the stencil up, I look at it under the microscope to make sure that all of the solder pads have plenty of solder paste in them. Honestly, that 3D printed jig worked pretty well, and I'll probably be using that technique in the future. I've got a box full of components, and now it's time to start putting all of these onto the boards. One thing I am doing different this time is using the interactive bomb tool from KiCad. It's just like a regular bomb, but when you click on a part, it highlights everything on the board to show you exactly where they are. There are boxes you can check when you've sourced the parts and then after you've placed them. Here's the moment of truth. I just finished assembling the custom PCB and I'm ready to test it out to see if it works. Instead of immediately connecting this to a solar panel, I'm going to use a benchtop power supply. It's worth mentioning that a benchtop power supply doesn't have the same power characteristics as a solar panel, but it'll work just fine for testing purposes. Like I mentioned before, the plan is to control the maximum power point by adjusting the resistance using a digital potentiometer and a microcontroller, but for now I just have it set at a constant value just for testing purposes. When I plug this in, what I'm expecting to happen is the charging indicator LED to turn on, and that will tell me that this thing is working. So let's go ahead and set the benchtop power supply to 24 volts, and I'll connect that to the board. Okay, so there's a problem. The charging LED is not coming on, and that tells me that the MPPT chip isn't behaving the way it's supposed to. Something is not right, so I need to start troubleshooting this. Okay, after looking at my schematic for a couple minutes, I immediately realized one problem. The current limiting resistors that I had in series with those LEDs were not the right value. They were way too high, which meant the LEDs were too dim to even light up. I went ahead and I swapped out those current limiting resistors, so now the LED should light up. Okay, it does not light up. That means that that wasn't the issue. I think it was a little bit wishful thinking that it was going to be that simple, but it's not. Clearly something else is wrong. So I'm going to keep going through my schematic and look through the data sheet to see if I can find something that I did wrong. All right, it has been a couple of hours of looking through the data sheet, looking at my schematic, and I think I'm on to something here. After looking through the data sheet, I found this list that is sort of all of the conditions that need to be met in order for the chip to function properly. It's sort of like a pre-flight checklist. So I started going through each one and I verified that all of them were working except for the very last one, and that's the battery temperature fault. The battery temperature circuitry just uses a voltage divider and a thermistor. When the thermistor gets too hot, the voltage goes down and it causes that fault. But I missed a critical piece of information. The thing that I missed is that I need an additional resistor in parallel with the lower resistor of the voltage divider. Since I was missing that resistor, the chip thought that the battery temperature was out of range and so it would not go into charging mode. I think the solution is pretty simple. I just need to add a 10K resistor in parallel with the lower half of that voltage divider, and I think the fault should go away. Okay, now I have that 10K resistor soldered onto the board, and it's pretending to be the battery temperature thermistor. When I plug it in, I expect that charging light to turn on. The charging LED has turned on, which tells me the MPPT chip is working, and I can keep moving forward. I'm so relieved that that fixed the problem. Now I can install the microcontroller and start writing some firmware for my MPPT algorithm. The algorithm is actually pretty straightforward, and if you want to have a closer look at it, I will have the code and all of the design files available on a GitHub page. The first thing I do is read the solar panel voltage using the ADC pin. Then I also read the current coming from the solar panel, and when I multiply those two values together, I get the power of the solar panel. The next step is to set the digital potentiometer, which sets the maximum power point of the chip. From there, I can just loop through those two steps over and over. I measure the power coming from the panel, and then I set the maximum power point voltage. This is called the perturb and observe algorithm. I make an adjustment to the maximum power point voltage, and then I see how that affects the power. If the current power that I'm measuring is greater than the previous power that I measured, then I know I'm on the right track. I just need to determine whether that increase in solar panel power was a result of increasing the VMP or decreasing the VMP. Whichever it was, I just keep going in that same direction. The other possibility is that the current power being measured was less than the previous time, so that tells me that I'm going in the wrong direction. If I increased the VMP last time, then I need to decrease it this time, and vice versa. It's worth mentioning that the perturb and observe algorithm is not the only way to approach maximum power point tracking, but it is probably the easiest to implement. I'm feeling pretty good with how this algorithm is working so far here on my bench, so now it's time to connect it up to an actual solar panel to see if it works. I'm back over here at the window next to the solar panel outside, and I've got it connected up to the MPPT charge controller. On the TFT display, I've got 4 values listed. From left to right, top to bottom, I've got the solar panel voltage, the solar panel current, the solar panel power, and then the 4th value is the digital potentiometer value, and it's a 7-bit value that ranges from 0 to 127. That digital potentiometer is what sets the voltage of the solar panel. For the load, I'm going to be charging a large lead-acid battery down at my feet. Right now, the battery is not connected to the charge controller, so you can see that my current is close to 0, and my open circuit voltage is about 21.5 volts. It looks like it's a little bit overcast today, and so that VOC value is going to change from minute to minute. So I'm going to go ahead and I'll connect up the lead acid battery, and we'll see that charge controller kick into action. I want you to keep an eye on that fourth value. That's the digital potentiometer. I'm watching that potentiometer value change as the power increases, and then it'll overshoot, and then the power will go back down, so then it backtracks and tries to correct itself. This really illustrates why you need an MPPT charge controller on a solar panel, because for about 30 seconds that sun came out, and the MPPT charge controller jumped all over it, and it started sucking out more power from that panel, whereas like a traditional charge controller would not have been able to adjust like that. There's so much more that this custom PCB can do. If you remember looking at the schematic, I also added power measuring circuitry to the load side. That allows me to measure the power coming from the panel and then the power going to the load, and if I compare those two numbers, I can calculate the efficiency of the charge controller. I also added separate terminal blocks for the battery as well as the load, and then on the load side, I can control whether that load is turned on or off with an additional MOSFET. That means I can have both a 12-volt battery and a 12-volt load connected to the charge controller at the same time, and I can turn the load on or off as needed. This project ended up being really challenging, and I think I bit off a little bit more than I can chew, but that's how I learn and I grow as an engineer. If you want to take a closer peek at the design files or the code that I used, I'll have all of that available on a GitHub page. That's it for this video. My name is Zach, and I'm the Byte Sized Engineer, and I look forward to seeing you next time.